Hi all. So in this video, we will show how to compute trajectories from three-dimensional velocity fields. So of course, these trajectories will no longer be on a plane, but they will generally be in a 3D space. The corresponding notebook is located inside the introduction folder, inside, of course, the 3D demos folder. No, actually, I just already opened it. So the notebook essentially computes the flow map of trajectories given a velocity field or unsteady velocity field in 3D. Now, the velocity field is of course assumed to be defined on a gridded domain. And in this demo, we choose the unsteady viscous ABC flow as an example. The first three steps, importing data, defining computational parameters, and interpreting the velocity field, are the same as in the demo on the computation of the velocity field. The last step simply computes the trajectory using the functions implemented in these this TBarrier notebooks. So I'll skip these first three steps because they're the same. Let's take a look at how to compute the trajectory. So first of all, in order to compute trajectory, we need to first import this function integration df dt, which you can find actually in the subfunctions folder and in the integration folder. So that's essentially this function here. This function simply takes as input, of course, the time over which you want to compute the trajectory, the initial condition, the x, y, z grid of the data, the interpolants of the respective velocity components. Then you need to define whether the velocity field has periodic boundary conditions or non-periodic boundary conditions, whether it is a steady or unsteady. And this final variable simply is used to then eventually print the progress during the integration. This periodic variable, it actually has four bool. So it's a list containing four variables. Why four? Well, the first three are simply for the spatial dimension, whereas the fourth dimension simply denotes whether you also have periodicity in time. Now, if for non-periodic velocity fields, this will generally be false, of course. Back to our main script. Now, of course, you can check this function here in more detail, but essentially, in order to do the integration, we use manually implemented Runge-Kutta integration step, which is again defined here, this function. Now, back to our main script. So what does this function need to have in order to compute the velocity field? So of course, you need to specify the time interval first. So we need to specify the initial time. Of course, it's not in days. The final time, which is also not in days, and the time step, which is also not in days. This is for the forward trajectories. Now, for backward trajectories, you need to have that. Of course, the final time needs to be smaller than the initial time, and the time step also needs to be negative. So one simple fix that you can do to optimize this, you can put np sine tn minus t0. This makes sure that, of course, if Tn is smaller than T naught, then this quantity here will be negative, whereas if it is bigger, then it will be positive, of course. Then, of course, you need to define this time array so you need to put these things together into a non-pair array, which is done here, and then you need to define the initial conditions. We need to simply pass all these arguments then to this integration dfdt function. And what this integration dfdt function returns is it returns two things. So the first one, this f map, is simply the flow map. So basically an array which stores the position of the trajectory at various times. And the second one is dfdt is simply the derivative of, so the time derivative of the flow map. And what this stores is essentially the velocity along a trajectory. If I compute this now, then of course this might take some time, but not too much actually, or it shouldn't take too much. Yeah, so 6.18 seconds actually. And I can now check out the shape of these functions. So print f map shape, print df dt shape. shape. So what they have is, so this dimension here is essentially the dimension associated to time. So of course, you will have one less, since you need to, so when computing the velocity field, you need to take derivatives. You will have one less value here in the time series, simply because of the computation of simply because you use finite differences when computing the derivatives. 3 simply denotes the spatial, the x, y, and z components, and 1 is because we've just computed one trajectory. Now, of course, I can compute multiple trajectories, similarly to what I did when I computed. So when I evaluated the velocity for the multiple points, one can also compute multiple trajectories at once. One can then also plot the trajectory, of course, and we will plot this trajectory here using this plotly functions, which is a nice visualization tool in 3D. So essentially here, this is the first, so this is the x component of trajectory, this is the y component of trajectory, and this is the z component of trajectory. So that's why 0, 1, and 2. This 0 at the end is because we just have one trajectory here, right? So we just have like one trajectory. Hence, we choose this to be 0. And you can see that there's this trajectory in 3D where this red spot simply indicates the initial position, and of course, the black evolving curve is simply trajectory. That's pretty much it. See you in the next video where we'll be then computing the gradient of the flow map from 3-dimensional velocity fields.